Hi everyone. Today we're going to be taking a look at an example kinematics problem. So in the last two videos we showed how to derive the four kinematic equations using two different methods, one only algebra and the second using calculus. And today we're going to be taking a look at an example problem. So solving an actual physics problem using these four equations. So the problem that we have today is going to be, okay, so the problem that we have today, there's going to be a car. Here's our car, and it skids to a stop at some point. So let's say this is the length of the skid marks that it makes. It skids to a stop, and the skid marks are 290 meters in length. The problem also tells us that this right here is when the car applies the brakes, and the brakes are going to provide a constant acceleration of negative 3.90 meters per second squared. So it hits the brakes right here, and this entire 290 meters, the acceleration is negative 3.90 meters per second squared. The problem asks us to determine the speed of the car before it began to skid. So what is the speed that the car has right here before it applies the brakes that provide the negative acceleration? So a couple things. Here's our drawing. It's traveling with some velocity VI at t0. And we'll call this x0. Here's some xf, tf at this location in space, the final position. At the final time, it has some vf equals 0 meters per second because it stops moving, right? It skids 290 meters and then stops. The final velocity is 0 meters per second. So we know that delta x is 290 meters. We also know that the final velocity, Vf, is 0 meters per second. And we also know the acceleration, negative 3.90 meters per second squared. What do we want? We want the initial velocity. We want VI. So we have three known quantities and we want one unknown. This can be solved using these four equations here. Particularly, looks like we can use this third one. Since there's no time mentioned, like it takes so long, it takes this amount of time to skid to a stop. There's nothing like that mentioned in the problem. We can use the time independent kinematic equation. So let's use number 3, which says the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the total displacement. Vf, we know what Vf is. It's 0 squared equals our unknown Vi squared plus 2 times negative 3.90 meters per second squared times 290 meters. Okay. This is the initial velocity squared is equal to, let's see, or sorry, rather, equal to the initial velocity squared minus 7.8 times 290. This is where we are after we plug all of our known quantities into the time-independent kinematic equation. Final velocity squared equals unknown initial velocity squared plus twice the acceleration times the total displacement. This entire quantity will be negative. Let's move it to the other side. The initial velocity squared is equal to 7.8 meters per second squared times 290 meters. It's simple to see we need to multiply these two numbers and take the square root of both sides to obtain our answer. So the initial velocity is going to be equal to 7.8 times 290 meters squared per second squared square root. And if you plug this into your calculator, you will see that it comes out to the initial velocity being equal to 47.56 meters per second. That's our solution to the problem. The car had a velocity of 47.56 meters per second at the instant before it hit the brakes and began to decelerate over 290 meters to a complete stop. This is an example of a very simple kinematic problem. We only had to use one equation. We were given 3 out of the 4 variables in the equation, and we just had to algebraically solve for the remaining one. There are more complex kinematic problems where we'll need to use more than one equation, or there are 2 steps to the problem. We'll take a look at some of those in the coming videos. Thank you for watching.